Hello everyone, myself Shubham Shiv. Today I am going to discuss about very interesting topic, hyperconjugation effect. Before going to start hyperconjugation effect, I want to discuss one question to make you realize how the important hyperconjugation topic is. Arrange the following in the increasing order of rate of electrophilic substitution reaction. What is electrophilic substitution reaction? A chemical reaction in which electrophile substitute a functional group, typically a hydrogen atom, is called electrophilic substitution reaction. We can take one example like electrophile will attack on benzene ring and substitute one hydrogen atom and make this product. We are not going to discuss the mechanism of electrophilic substitution reaction. So higher the electron density in the ring, higher will be the rate of electrophilic substitution reaction. On the basis of plus I effect, we know that the order of plus I effect among these, the T-butyl group has higher plus I effect group, then isopropyl or we can also write as a then ethyl group, then methyl group. So T-butyl group has higher plus I effect, so it will push more electron density into the ring. So the order of electrophilic substitution reaction is like D, then C, then B, then A, because the order of plus I effect is like this. So on the basis of plus I effect, the answer is this, but this answer is wrong because there is a role of hyperconjugation effect. We will come back on this question after discussing the hyperconjugation effect. Before going to discuss the mechanism of hyperconjugation effect, I want to introduce about alpha hydrogen. What is alpha hydrogen? Take an example like of the carbon attached with a functional group is called alpha carbon. Functional group may be ketone, the carbon attached with a functional group is called alpha carbon. So this is alpha carbon and here this is alpha carbon. Take more example like ethene, alkene. So this is functional group, this is alpha carbon, and the hydrogen attached with alpha carbon is called alpha hydrogen. So here how many alpha hydrogens? 3. here alpha carbon, and this is alpha hydrogen, this is alpha carbon, and this is alpha hydrogen. And similarly here, this is alpha hydrogen, this is alpha hydrogen. In this case, in this example, this is alpha carbon. In the case of hyperconjugation, we only focus on alpha position. There is not any kind of role of beta position. So we only look at the alpha position. Find the number of alpha hydrogens. So this is functional group. The carbon attached to a functional group is called alpha carbon, and the hydrogen attached with a alpha carbon is called alpha hydrogen. So how many alpha hydrogens are here? 3 and 2, 5. And here only 1. And in this example, here 3, because this is CH3 group, this is also CH3 group, and this is also CH3 group. So how many alpha hydrogens are here? 3, 3, 3, total 9. And in this example, how many alpha hydrogens for this alkene? CH3, CH3, and this is CH2 group. 3, 3, 6, this is also alpha position. Then total 8 alpha hydrogens are here. Now I am going to start what is hyperconjugation. This effect is nothing but this is just conjugation of sigma bonded electron with p orbital or pi star orbital. Take an example of ethyl carbocation. This is empty p orbital. Carbocation is an electron deficient species. So it wants to electron, it needs electron density to gain stability. So what it will do? It will interact with alpha CH bond. This empty p orbital, carbocation has empty p orbital, so it will interact with alpha CH bond to gain more stabilization. So what will happen? This CH bond will break, and there is a formation of new pi bond between these two carbon. This structure is called hyperconjugative structure. This empty p orbital will interact with alpha CH bond, and this CH bond will shift here and form a new structure which is called as hyperconjugative structure. And hyperconjugation effect has another name. There is no bond between this carbon and hydrogen. So this effect is also known as no bond resonance. No bond resonance. Why resonance? because there is a conjugation of electrons. So all the CH bonds are equivalent, so each CH bond will show hyperconjugation effect. To distinguish the hydrogen, we can give different number H1, H2 and H3. Here what will happen, CH1 bond will break and form this structure. So this is H1, this is H2 and H3. We can also take CH2 bond. So CH2 bond will break and form this structure, and CH3 bond also break. So how many hyperconjugative structures are there? So there is a formula, number of hyperconjugative structure. It is equal to number of alpha hydrogen plus 1. This is the simplest formula to calculate the number of hyperconjugative structure. So how many hyperconjugative structures are there? First see how many alpha hydrogens are there. 3, 1, 2, 3. So 1, 2, 3. Here 3 structures, 3 alpha hydrogen plus 1. What is this one? This is the original structure. In the case of hyperconjugation, we also count the original one. We also consider as a hyperconjugative structure the original structure. Now we will see the example of alkene. Here sigma 2 pi, empty pi, this is filled and this is empty. Sigma 2 pi conjugation happens. In the another example, sigma 2 pi star conjugation. Take an example of any kind of alkene like this. Whenever pi bond forms, along with pi star molecular orbital also forms. So C double bond C has one sigma bond and pi electron density. This is pi, this is empty pi star. So whenever pi bond formation take place, along with 2 molecular orbital forms. One is pi which is filled and pi star which is empty. So this is functional group. The carbon attached with the functional group is called alpha carbon, and this is alpha hydrogen. So it will also interact with this empty pi star orbital. Alkene has empty pi star orbital. So this sigma CS sigma bond will shift here and this pi bond will break and form a new hyperconjugative structure. Similarly, these two hydrogen also show the hyperconjugation effect. So how many hyperconjugative structures are there? 3 alpha hydrogens plus 1. We are also counting the original structure. So 4 hyperconjugative structures are possible there. Find the number of hyperconjugative structure. So find the total number of hyperconjugative structures. So number of hyperconjugative structures equal to number of alpha hydrogen plus 1. So first we are going to count number of alpha hydrogen. So this is functional group, this is alpha position, so this is alpha hydrogen. So 2 alpha hydrogens are here. So total number of hyperconjugative structures 2 plus 1 3. And how many alpha hydrogens are here? 3. This is CH3 group, this is CH3 group. 3 3 6. So total number of hyperconjugative structures 7. And here 3 4 ja 12. So 12 alpha hydrogens. So total number of hyperconjugative structures 12 plus 1 13. Because we are also counting the original one. And here 3 3 3. So total 9 alpha hydrogens. So 9 plus 1 10. 10 total number of hyperconjugative structures are formed here. And here only 1 alpha hydrogen. So 1 plus 1 2. 2 hyperconjugative structures. Here 1 alpha hydrogen and 2. So 2 plus 1 3. We don't count this hydrogens because this is beta position. We only look at the alpha position. Now we will do the discussion of we will discuss the application of hyperconjugation effect. The first important application is stability of carbocation. Take an example. The carbon of carbocation is electron deficient, so it wants electron density. So what it will do? It will interact with alpha CH electrons. So if the number of alpha hydrogen increases, then the interaction of, or we can say the delocalization of positive charge is also increases. So the stability of carbocation is directly proportional to the number of alpha hydrogen, or also we can say it is directly proportional to the number of hyperconjugative structures. take example, this is methyl carbocation and next one is ethyl carbocation, isopropyl carbocation and T-butyl carbocation. So the stability of carbocation is directly related with the number of alpha hydrogen. So how many alpha hydrogens are here? 0, because it has no alpha carbon, alpha position. How many alpha hydrogens are here? 3, and here 6, 3, 3, 6, and here 9. So greater the number of alpha hydrogen, greater will be the stability of carbocation. So the stability order like this. Because greater the delocalization of positive charge increases the stability of carbocation. The next important application of hyperconjugation effect is stability of alkene. In the case of alkene, alkene has two bonds, sigma and pi. Pi bond is dense. Pi bond is electron rich bond. So take example like, of any kind of alkene like this. So pi bond has higher electron density. Higher the charge, higher will be the energy. If charge is high, then energy will also high. So by the delocalization of charge, we can increase the stability of alkene. Because pi bond has negative charge, so it needs the delocalization of charge. So the stability of alkene is also directly proportional to the number of alpha hydrogen or number of hyperconjugative structure. So this is simple ethene. So how many alpha hydrogens are here? 0, here 3, here 3, 3, 6, here 12. And how many hyperconjugative structures? 0 plus 1, 1, 3 plus 1, 4, 6 plus 1, 7, 12 plus 1, 13. So the stability of alkene is directly related with the number of alpha hydrogens and number of hyperconjugative structure. So the stability order is like this. Now I am interested to discuss the previous question. This answer is wrong according to the hyperconjugation effect. And one more important thing, hyperconjugation effect always dominant over the plus I effect. Note that point, hyperconjugation effect always dominant over the plus I effect. So what is the right answer of this question? Just take any kind of aromatic system, and how the hyperconjugation affect this aromatic ring. So this is the functional group. So this is alpha carbon. So this is alpha carbon. So here also the hyperconjugation effect is valid. So the new hyperconjugative structure is like this. And this charge will delocalize with para position. So in this case 3 alpha hydrogens are present, and in this case 2, and in this case only 1 alpha hydrogen is present, and here 0 alpha hydrogen. Greater the alpha hydrogen, greater will be the charge in the ring, because thus alpha CH bond delocalizes with pi bond of aromatic ring. So it will increases the electron density in the ring, and we know that electrophilic substitution reaction is accelerated by electron density in the ring. So it will depends on the electron donating group. So according to plus I effect, this is strongest plus I effect group, but according to plus hyperconjugation effect, here 3 alpha hydrogen. So here it will push more electron density into the ring. So what is the order of electrophilic substitution reaction? A, B, C and D. This is the correct answer. So whenever in question both effects will applied, so we consider only hyperconjugation effect, because hyperconjugation effect is dominant over the plus I effect. One more application of hyperconjugation effect is dehydration of alcohol. What is dehydration of alcohol? Removal of H2O molecule, removal of water molecule. Take example. So what is dehydrating agent? KOH, alcoholic. So here we can see that here the two possibilities for water. So for removal of water, it has two possibilities. It can, this OH also can combine with this hydrogen or also can combine with this hydrogen. So two possible products can be formed. So my question is, which one is major product? So on the basis of hyperconjugation effect, we can answer also the major and minor product. Greater the stability of product, greater will be the amount of product. So between them, which one is more stable? So we can answer on the basis of hyperconjugation effect. Here this alkene has 6 alpha hydrogen and this alkene has only 2 alpha hydrogen. So how many hyperconjugative structures are there? 3, and here only here 7. So we know that stability of alkene is directly proportional to the number of hyperconjugative structure. So which one is major? This is major and this is minor. Thank you. Okay, ma'am.